In this lecture, we're going to discuss random variables and probability distributions. We will focus on distribution approximations. In terms of the agenda, we will discuss how approximations work with distributions. We will then talk about the normal distribution as an approximation to the binomial distribution, and then the normal distribution as an approximation to the Poisson distribution. There are certain situations where we can use one distribution to find probabilities in place of another. The replacement distribution will not yield exact probabilities, but should be real close. We call these distribution approximations. So there are many cases where this is appropriate. We will focus on using the normal distribution to approximate both the binomial and Poisson. So why do we do this? We can always just use the exact distributions. Sometimes probabilities from discrete distributions do not yield an exact quantile. Other times it is just easier to model with certain distributions and explain the results than with others. So in some situations, especially hypothesis tests and confidence intervals, we will need to find the xth percentile. This will always work for a continuous distribution. It may not always work for discrete distributions. Here is an example. Say that we have this specific distribution and we would like to determine the 95th percentile. In other words, we wish to find the value from the binomial distribution given that leaves 95% of the data less than or equal to it. So for x equal to 17 from a binomial distribution, we get a value of 0.928611. For x equal to 18, we get 0.966556. So in this case, you can see that the value that is the 95th percentile would be somewhere between 17 and 18. For discrete distributions, only integer values exist for x. So now what? We will approximate the binomial distribution with a continuous distribution, preferably the normal distribution. In order for this to be valid, certain assumptions must hold. They are that the number of successes and failures in the data must both be greater than or equal to 10. If this occurs, we can state that the random variable x comes from a normal distribution with the mean and variance based on the calculation from the binomial distribution. This is because if we allow a success to be labeled as x sub I equal to 1 and a failure to be labeled as x sub I equal to 0 for each of the I trials, then capital X is just the sum of the x sub I. We also know that sums of random variables tend to normality. Here is a simulation. We can see that as n times pi approaches 10, the distribution is becoming more and more symmetric. Let's go back to example 1 and use the normal approximation. Here are the solutions. Notice that the first thing that we do is check the assumptions. Remember that we need for both the number of successes and failures to be greater than or equal to 10. You can see here that this occurs given that they are 13.5 and 16.5 respectively. We can then find the mean and standard deviation for the normal distribution as given on the slide. Now let's use the normal distribution to find the 95th percentile. So we are looking to solve the formula on the slide for little x. We will go to the z table and find the given probability. Then we will determine the value for z from the outer vertical and horizontal columns in the z table. In this case, we find z equal to 1.64. Now we use 1.64 and the given information to solve the z-source equation for x. In this case, the 95th percentile is 17.969. The approximation seems to work well considering what the binomial distribution told us. Let's try another example. Here is another example based on seatbelt use. Question 1 expects you to show that the normal approximation holds. Question 2 wants you to find the probability that the number of drivers that wear seatbelts fall between 180 and 230. Finally, question 3 is asking you to determine the 90th percentile, or what value does 90% of the number of people that wear seatbelts fall below. Let's look at question 1. To accomplish this, we need to see if the number of successes and failures is greater than or equal to 10. Based on the calculations on the slide, the number of successes equals 200 and the number of failures equals 300. So the assumption is met. Now let's move on to question number 2. First, we will need to find the parameters for the normal distribution. Based on the binomial, we get a mean of 200 and a standard deviation of 10.95. Now we can use the parameters to find the probabilities. we first need to find the z-scores for each x value. These are given on this slide. If we look up those values in the z-table, we get probabilities that are given. Finally, to get the in-between probability, we will subtract the smaller probability from the larger. The probability becomes 0.9633. Now let's move on to question number 3. For question 3, we would like to know what the 90th percentile is. We can find the z that corresponds to 0.9 in the z-table. We determine this z value to be 1.28. Next, we can rearrange the z-score equation to get x. Based on the results here, we get x equals to 214.02. Now let's summarize this example. Here is the summary. For number 1, the assumption holds since the number of successes and failures are greater than 10. For number 2, the probability that x is between 180 and 240 is 0.9633. And finally, number 3, the 90th percentile is 214.02. Now let's talk about the normal approximation to the Poisson distribution. In order for this to be valid, lambda needs to be large, usually greater than 20. From the Poisson, we know that both the mean and the variance are equal, and they're equal to lambda. So we can write this as a normal distribution with mean lambda and variance lambda. So why does this work? Well, normally when lambda is small, we cannot develop the left side of the bell-shaped curve. This is because the minimum value that the Poisson distribution can take on is x equal to 0. As we increase the size of lambda, we get more room for the left side of the curve to develop, since there will be more values between the mean and 0. Let's look at a simulation of this. Here are the plots of the simulations of data from a Poisson distribution of size n equals to 500. For each plot, we use lambda equal to 1, 10, 50, and 100 respectively. You can see for the plots where lambda is equal to 1, the data start to bunch up near 0 and 1. If we smooth this out, then it seems that we can only get half of the bell-shaped curve. Notice that as lambda increases, the curve becomes more bell-shaped. Also, notice the values on the left of the histogram. For the upper left corner plot, the values go down by almost to 0. By the time we get to the lower right corner, we are starting that low left side at around 80. Now let's look at an example. So basically here we have lambda equal to 26.692, and we wish to determine the probability that for the next week we will see less than or equal to 24 parking tickets. First, we will do this with the Poisson and then the normal. So for the Poisson distribution, we assume that lambda is equal to 26.692 and determine the probability. In this case, we would need to sum the probabilities from 0 to 24. That would be crazy to do, let alone type out. So based on software, this probability is 0.3455. Now let's try it with the normal. So first we need to find the mean and standard deviation for the normal. Since we assume that the mean and the variance are equal, we will set the mean to 26.692 and the standard deviation to the square root of that, which is 5.166. Now we get the z-score on the screen. Now we follow the procedure to find a probability from the normal distribution and get 0.3015. So the difference here is about 0.04. So is the assumption okay to use? Well, it depends. It depends on what a difference of 0.04 makes. Now, in the above examples, we were given values for the parameters. But what do we do if we're actually given raw data? So if we were actually given data, we would need to get a baseline. We could then use it to estimate the parameters for the distribution. In this particular case, lambda. But since count data is closer to continuous than binary data, couldn't we just check the raw data for normality? Well, of course the answer is yes, and that's what we would normally do. So we can accomplish this by running a normality test or creating a normal probability plot. The main difference will be with the variance. The variance for the Poisson is equal to the mean. In this case, we would just use the standard formula for finding the variance of the raw data when using the normal. The closer this value is to the mean, the better the approximation. Let's look at an example. Let's go back to the parking tickets. Now suppose that instead of the summarized results, we actually got the raw data for the last 26 weeks. Let's check to see if we think that the data could come from a normal distribution. Then let's compare the variances to see how good we think the approximation will be. Here is the normal probability plot. It does seem to hug the line, and the p-value is 0.4743. Now, since the p-value, which was 0.4743, is greater than 0.05, we conclude that the data does indeed seem to come from a normal distribution. Now let's compare the variances. From the data, we can see that the mean is 26.692, which based on the Poisson distribution also means that this is the value for the variance. If we look at the variance calculation on the raw data, it is 19.982. So now what do? Since it passes the normality test and the variances are probably not similar enough, I would probably just use the normal distribution as usual.